Okay. So that'll be cool. So I'm going to do that. And I finally got my PA system into my Stacy and I are going to hang out and do that. I bought her a piece of he's a walking plant with that. Paint pictures around the house. That sort of stuff. I'm sure I'll be put to work for a little bit. So, on that, you just do this spare a little bit. But try to put out. Yeah, I keep telling myself that. I feel guilty sometimes. I used to work 10 hours every day. You know? Yeah. I don't have to do that. Especially if you take that out of the video. Okay, you guys ready to start up? Let's do it. So I'm going to walk you through a little bit of this again. Just remind you where we're at. We want to answer maybe this question. What's mu if I didn't know what sigma squared was? And I can encode it either as a sigma squared or a phi. It's just flipping over the definition. So if sigma squared was a 5, right here, phi would be a 0.2. And I have the exact same sampling distribution. I don't have to change anything. That's the same sampling distribution. You are not allowed to integrate under your likelihood functions until you call that thing a random variable. That's when you need the decoding. So because you're going to integrate space. You're adding up space, and when you take a transformation, you warp space. So you warp the area. If you guys want a full-blown lecture on that, I'd be happy to do one in a review session if it's requested. So again, it's just the chain rule. It's the fundamental theorem of calculus with the chain rule added to it. It's the way that always comes out. That's why we have that absolute value on the Jacobian. I always remember that being pretty poorly explained to me, what was happening in my probability classes. So if you want me to clarify that, I can. It would be good to get a video on that, so I can just say, watch this video. Anyway, for likelihood functions, you're allowed to just reparameterize. You don't need to do anything. For probability distributions, or things that you're integrating under, you need to warp the space. And that's the derivative term. And that's warping the area of the space. So a lot of times we're interested in what do we think mu is. And I don't want to tell you what I think phi is or sigma squared. And so what a Bayesian does, it's always the exact same thing, because they're always working with a probability distribution. If you know your probability calculus, being Bayesian's pretty easy. So if you know how to do probability, because everything is living in a probability space. You'll hear a lot of Bayesians go off on measure theory because of this, instead of asymptotics. And I kind of mitigate that in this class. You know, we don't need to talk about it that way, but there are kind of more theoretical underpinnings to what we're doing. So if you want to get rid of a parameter and not condition on it, you need to upgrade it to a random variable and integrate it out, marginalize over it, average over it. And Bayesians can do that pretty easily. Computationally, if you have an MCMC, markup chain Monte Carlo, which I'll teach you about later, marginalizing something is as easy as pi. I mean, it's just the simplest thing in the world. So these integrals turn out to be really easy to solve computationally. And I'll show you how to do it later. So this is the problem we might want to study. If I wanted to know jointly what mu and phi were, I would try to study this distribution. If I had this distribution, I could find the conditional distributions by dividing by the margin. I could find the marginal distributions as well. So with the joint distribution, you can do everything. It has all the information. Most of that information is coming through the likelihood. At least it should be. So the prior should be acting as a penalty in some way that doesn't overtake all the data and all the analysis. So this thing right here is just going to be the likelihood of mu and phi. And when I write it like this, I mean that I want the joint likelihood. So I'm going to be studying this as a bivariate function of mu and phi. And somebody asked a question about that a couple weeks ago. And then I'm going to multiply it by my priors. So pi mu. And I'll just be more specific. I'm going to write it down jointly like this. That's my prior. And I could try to work out this integral. You won't have much luck in this problem. We'll see why in a second. Pi mu and phi. I integrate over both of those parameters. Get rid of both of them. So this is a double integral. And I'll write it correctly. This goes from 0 to phi, or 0 to infinity. We're integrating over phi first, and then mu. A lot of times I just write one integral sign. So oftentimes I have problems that I'm working with, and there's a lot of parameters. And I don't just stack integral signs here. I usually write one, and I say I'm integrating over the whole space. And then I make some notation for the d over there. You'll see that. That's pretty cool. So if you see me do that, and I'm integrating over two things, and I just pop one integral sign, that's a typical convention. You know, it's only after you get past your vector physics class, you know, where you're integrating over three things and you have the three integrals, and after that you get tired of finding out the integrals. That's been my experience anyway. So this is what we're doing. So we're just taking the likelihood function, we're multiplying it by our prior. We chose for this analysis this to be equal to pi mu times pi phi. We at least made an argument that knowing mu, if I told you that before I show you any data, it doesn't tell you anything about phi. And if I told you what the variance or the precision was, that shouldn't be telling you anything about mu. That's a priori beliefs. Now, I will point out, this thing doesn't factorize no matter what you do, even though I have the prior factorizing here. So I'm saying my prior beliefs are independent of each other. I'm not going to inject any joint information. You could, and we'll see a problem where we will. I'll at least point to it in this class. But very typically factorize that. There can be properties you want from the joint distribution, and you have to invoke those properties jointly in the prior. So remember, the prior has knobs, and I can steer properties of the posterior through the knobs of the prior. So I could do things jointly and come up with joint properties by building a joint relationship. I'll say, if you look at this right here, the kernel of the likelihood, you can already see that the posterior will not factorize. You will never be able to untangle that mu from that sigma squared, or that phi from that mu. They don't factorize. If they factorize, they don't have information about each other. But they do have information about each other through the data. The data is supplying information about both of them, and there is joint information about those. And I'll show you what it looks like a little bit later. I'll show you what that joint distribution looks like. You might have some mild confusion by other classes that you've taken. And you might think, no, I learned when x was normally distributed, the test statistic, s squared, minus, I'll say, x bar, over n minus 1, is a sum from 1 to n, and x bar, sum of the xi's, over n, I goes from 1 to n. So just the mean, just the sample variance. A lot of people call this sigma hat squared. It's an unbiased estimator for sigma hat, or sigma, sorry, sigma squared. It's an unbiased estimator for sigma squared. Take the square root, it's a biased estimator for sigma. So, this one is an unbiased estimator for mu. Sometimes we like that unbiased thing. So a lot of people have been working with these test statistics, and we'll work with these in this problem as well. But there's going to be an important distinction that the Bayesian makes. the posterior distribution of mu and phi, or mu and sigma squared, for the exact same reasons, it does not factorize. They have joint information about each other. These two test statistics are independent of each other. And so a lot of people learn that. So they are independent. And in chapter 5 of Casella and Berger, if you've taken the inference class, they'll prove that to you. This turns out to only be true for normality. I didn't know that a little while ago. Probably I learned that like a decade ago. And I was astonished I'd gotten through my PhD and did not know that that was true for other types of data. Yet a lot of times we take something that's normally asymptotically normal, asymptotically chi-squared, we divide by it, and we get a t-distribution. And if it's anything but normal data, those are not independent of each other. It's kind of interesting. So there's an instant violation for non-normal data when you end up doing that standard form. How big of a deal is it? Probably not that big. So again, S squared, this test statistic for estimating sigma, so this is approximately sigma squared, and this one's approximately mu. The law of large numbers says that this converges to mu. It says it in the strongest sense. So if you know about convergence, it converges almost shortly. Okay? So it gets there. It's also normally distributed. And that's kind of cool. So it tells you how much it jumps around, how much variability you see with it. And that normal distribution describes that. So it doesn't just converge. It converges and the variances get smaller and smaller, and the variances are estimated by this. So as n gets bigger and bigger, this thing converges, and then the total variance of the process here is controlled by s squared divided by n. We'll see that parameter pop up in our Bayesian analysis. So again, we're just kind of talking about classical choices, possible misunderstandings. Mu and sigma are not independent of each other, but the test statistics are. A Bayesian does not just study test statistics, they study posterior distributions. So a classicist, an asymptotic classicist, some people call these frequentists, but I would like to end that because a Bayesian can be a frequentist. We've seen that in our homework one. Bayesian can be a very good frequentist. It can be the optimal frequentist. But a lot of times in classical stats, they study properties of the sample. They talk about how much it's expected to vary. And the Bayesian is talking about the underlying parameters, and they're putting a distribution on them. And inherently, that's different. It can lead to very similar inferences, but at times it can be very different. We'll see some overlapping commonality today. So I think this is where we were last time. We just wrote down this prior. I ended up picking this to be proportional to 1. If I have proportionality upstairs and downstairs, those things will cancel. So I could have made this proportional to 10, proportional to 2.2, just something positive. In this, we kind of like this prior, 1 over phi. And this was the conjugate limit of a gamma. So this right here looks normal. Normal, it's centered somewhere, and sigma naught squared is going off to infinity. And that's how we rationalized it. So the conjugate prior on mu was normal. As I take the limit, it flattens out that distribution. This is an idea right here, it's concept. This is a flat density. It is improper. This one right here came from gamma, alpha naught, beta naught, and this went to 0, and this went to 0. So if you like thinking about conjugate limits, you can think about it that way. This is the limiting process of that. This posterior here will converge to something as these parameters go to something. If you don't like working with anything improper, if you don't like infinities and driving things in a limiting process to 0, pick this number to be the largest number in the world that you've ever heard of. or could find or discover, and raise that to a lot of powers, and you'll get something very similar to the limit. Just take a limit. It makes life easier. Okay, so that's just a bit of discussion, some background about things you already know. Stephen said he has good reason to believe this might be a t-distribution. And we worked through this, and Stephen's about right. It's just that this fails a particular test. And I'll talk about it in a moment. But if we just work through this and just plug in the likelihood times the prior, and I'll get rid of the normalizing constant, then this thing is just the integral from 0 to infinity. I'm integrating over the precision because I just want to know about mu marginally. Tell me what you think the average is. And so this is going to look like the likelihood times the prior. So the likelihood will look like this, 1 over 2 pi square root. I'll put my phi in here to the 1/2 e to the minus phi x ops minus mu over 2 squared. And then there's the prior. And I'm writing down 1 times 1 over phi, so that's 1 over phi. We have good reasons to think about this prior. We talked about scale invariance, we talked about conjugate limits, and I'll give you more reasons down the road. And so all we need to do is integrate this thing. This looks like a particular gamma. I'll just rewrite it. This was the question at the end of class last time. Where did the prior go? I soaked it up in one step, so I'll just write this down. By the way, I can get rid of my normalizing constant because I've already written this up to proportionality. I've ripped off the normalizing constant of the posterior, of the joint posterior. So I'm just going to write this up to proportionality, start chucking my constants. Phi to the 1/2 minus 1, that's this, that's right here. That was the small confusion at the end of class last time. So I just soaked that prior up here, and lo and behold, that little magical -1 shows up. I like it, it always does. So this is minus phi x ops minus mu squared over 2 dp. And so I recognize this instantly because I'm a good Bayesian and I know what my distributions look like, I know what kernels look like, I know what the normalizing distributions of those distributions are, at least the parts that matter. And so instead of going through some sort of continuous parts argument and trying to work through this thing and expressing it in terms of gamma functions, because you'll never be able to write this down explicitly. So I just know what the answer is. It's the inverse normalizing constant to a gamma. So this looks like beta twiddle, alpha twiddle, over gamma alpha twiddle, gamma function, and I invert this. Where this thing right here is alpha twiddle, and this is beta twiddle. So this whole thing looks like a gamma with 2 parameters. Those parameters are alpha twiddle and beta twiddle. Normally I put this right here. So because I recognize this as a gamma, and I know properties of my distribution, if it had the integrating constant, it would integrate to 1. It doesn't integrate to 1 because it doesn't have the normalizing constant, so it integrates to the inverse of the normalizing constant. If I inverted this thing and I threw it here, it would integrate to 1. So rather lazy in my integrations because I'm dealing with things that always add to something I know what they add to. So we like that scale, it makes everything easy. So here's our answer to this integral, at least it's proportional to this. So let's just write it down, what we just found. This looks like this. So pi mu, given x ops, is proportional to gamma. Alpha twiddle was 1/2. And then my beta twiddle. So beta twiddle looks like x obs minus mu squared. There's a divided by 2 in here, if you'd like to keep it. And this is going to be raised to the 1/2 power. That's alpha twiddle. So again, I'm just pattern matching. I'm in cruise control right now because I know my distributions. So this is proportional to. This is a constant. This is a constant. I've been writing this up to proportionality the whole time. I could have carried it all with me and had the correct normalizing constant. Turns out you can't in this example because the first normalizing constant we chuck blows up to infinity. We'll see that in a moment. If I did keep them all, it wouldn't change what the kernel of the distribution is. And what I'm doing all the time is I'm just recognizing what the kernel looks like. And then I know where the parameters are. So this looks like this. 1 over, this is a quadratic to the 1/2, that's absolute value. X obs minus mu, absolute. Again, this is a distribution on mu, right here. So we can kind of see what this looks like. This thing looks like this. So pi mu, given X obs, mu. This is going to be centered at X obs. And it looks like this. So it peaks right there at X obs. And then decays. And it exponentially, quadratic or hyperbolically decays. It's a hyperbole. And so we already know that things like 1 over, I'll just write it down. We know sum of the 1 over z, z goes from 1 to infinity. This goes to infinity. It blows up. You learned that in your first couple weeks of calculus class when you're working through infinite sums. You can come up with the sandwich theorem, and prove that, and do other proofs. But for the exact same reason, this thing right here, if I ended up looking over, mu goes from minus infinity to infinity, 1 over x obs minus mu, absolute value, d mu. This can diverges. So that posterior is useless to us. So we've been arguing maybe priors being improper or fine because we're not going to do any analysis off of them directly. We're going to slide it through the likelihood function, and the likelihood might bring down the tails on everything. Hopefully the data has the information about the tail behavior, not your prior. This thing blows up. We want probability distributions. We argue it's nice to be a Bayesian because I get things between 0 and 1 and I can interpret them as probabilities, conditional probabilities on the data. But here you don't even get that. So you don't get a posterior with this. So that's kind of troubling. It's like this is junk. And that's too bad. Let me tell you a theorem real quickly about proper posteriors. How you can assure your posteriors are proper. Now this may or may not be a good idea, but it's good to keep in mind. If the maximum likelihood estimator exists, so MLE, I'll just describe it very generally to you to think about the side problem. So I'm going to recycle some notation. We'll come back to this problem in a moment. Here's a side theorem. Might help us. 0. That makes it seem like it's important, right? So remember, what's a theorem? What's a lemma? What's a corollary? And it's like, well, it depends on their importance to each other and which one came first. This is supposed to cue you in. I might ask you this on a midterm or something like that. So if the max likelihood estimator exists, so I'll just draw you a picture right here. Let's imagine I've got some likelihood function. It's on some parameter theta. I've got some data. So this is just the likelihood. This is the function over theta. Let's say my likelihood looks like this, right here. It peaks right there. We would say this value right here is the MLE. It's the argument that maximizes the likelihood function. This is the max likelihood. So usually we write something like max over theta, the likelihood. That's that value. This is the argument that maximizes the likelihood. So commonly we'll write arg max theta of the likelihood. Slight distinction between the max likelihood and the maximum likelihood estimator. So a lot of times people are doing inferences using their MLE. Bayesian takes it a step further and they do their inferences times of the money, based off the likelihood times a regularizer, times a penalty function. So to dictate for good reasons, hopefully, i.e. a prior. So if the max likelihood estimator exists, then, and I'll say this, if your prior is proper, i.e. it integrates and is normalizable, i.e. it's an actual probability distribution, i.e. it does not diverge when I take the integral over it. So normalizable, so I'll write down pi theta d theta is equal to 1. And I don't really care if you make it proportional in our analysis. We usually throw everything away, so the kernel of that distribution needs to be integrable. So if your prior is proper, then your posterior is proper. If your max likelihood estimator doesn't exist, that's like it lives on the boundary of the space and you're asymptoting into it, but you never get there, be prepared for your analysis to have some issues. So the boundary effects can be problematic. So if this is a problem for us, it's a problem for everybody else. Okay, so I'm not going to say that all posteriors are proper, and you have to watch what you do in semi-parametrics when you build likelihoods. You can make some likelihood functions that don't have maxes. You gotta be careful if you build too much flexibility into your model. Okay, then your posterior is proper. Proof, pretty easy. There's a bit of an embellishment. So if I just look at my posterior distribution, given x, if I want to show that this is proper, then I just need to think about integrating its kernel. Its kernel is represented through the likelihood function times the prior. So this is proportional to pi theta, likelihood theta, given x, pi theta, d theta. I'm integrating over the entire world of theta. This thing is going to be bounded by, and let's give this a name. I'm going to call this thing L hat, MLE. So it's the likelihood evaluated at the maximum likelihood estimator. It's the peaky version, peaky thing. So this is going to be L hat bounded, MLE. Everything is less than this value. So So when I go to integrate under it, everything is, this is certainly bigger when I'm integrating over this rectangle. So times pi theta, d theta, this is going to be equal to L hat and LE. Again, if I just had the kernel of the prior, it would integrate to something that is constant. Again, I'm integrating over the whole space of theta. Let's say we've normalized this so it's 1. Or it's a constant if you haven't normalized it. So, and it's normalizable because it's proper. And so if my priors are proper, your posterior is proper, assuming you have a well-behaved likelihood function. And while there's some fringe cases out there that we could study, it's probably more important to study problems first where there aren't all these fringe cases. So pretty much in your experiences, your likelihoods have been normalizable. If you'd like an example of a non-normalizable likelihood, imagine a Poisson distribution. So it's this counting thing. We'll study them next. Give you some more distributions, more playing around with the same stuff, applying Bayes. But Poissons are counting distributions. It's your fundamental counting distribution. It's where all the other ones come from. Limits of them, mixtures over them, so on and so forth. But if you ended up sampling from a Poisson once, and you saw 0 count, and you use that as your likelihood, that thing is improper, and you can convince yourself of that. So it does happen. It's usually like when you don't have much data. Okay. So what I just told you is that we used improper priors, and we came up with an improper posterior. So let me just ask you, here's my question. We came up with this answer a minute ago using improper priors. Look like this. It's got shape. That's kind of cool. But it doesn't integrate, so you can't consider it a probability measure. You can't use it to make a probability measure. You can't express things in terms of probability, and I thought that was the whole point. That's like one of the big deals. So you put it on a measuring stick, and you can measure if it's big or small. I like that. I really like that. So, question. How should we proceed in our example? And I'll say hint, we want a proper posterior. The end game of for a Bayesian is to get posteriors and estimates based off of posteriors. That's what all Bayesians have in common. It's different types of Bayesians depending on how you construct your priors. We'll talk about that further into the class. But we're all coming up with posteriors and interpreting everything on this probability scale. Hint, we need a proper posterior. One of my very favorite things to do when I go to conferences is to go to the poster session where a lot of graduate students are presenting their work. It's usually a mixer attached to it, so it's fairly loose. Everybody's friendly, looking at each other's posters. People are gathered around. Graduate students are trying to make this really good impression because they want a job later on. They're trying to meet people, trying to build network. You can go up and you can see the Bayesian thing, and it's look at it and go, oh, your posterior is improper here. It will freak them out. So even if it's not, you know, whoa, let me think about this. It is a fun game to play. Yeah, I can see right here, and it's like, I think you're just giving us random name. I'm just kidding. So, but if you accuse a Bayesian of having an improper posterior, you will freak them out for a second because they'll realize they might have some huge mistake. It has happened once in my career where I was working on a research project. We built up the whole MCMC, everything, and everything's just going wrong, so we think we have an error in code. It's not able to sample because there's not a probability distribution and the sampler is running up and down the tails. And so exactly what you would expect if you're trying to sample from a non-probability distribution. I had an improper posterior, the code was right. And so I needed to think harder about my prior choices. There was an interaction between the priors. So as one of the parameters went down, the other one could go up artificially. And so it led to this behavior that flipped the tails out too much. Anyway, solvable problem. Somebody had solved it already. I finally found their solution. This was a known problem, and I fixed my stuff and got published later on. So, can happen, you need to look for this. You'd be able to guarantee people you have a proper posterior. Jane? Yeah, this is just, that was the tippity top of the maximum likelihood. So this was, when I drew this, MLE. Maybe a hat on that. This was L hat, MLE. That's the likelihood evaluated, the MLE. Too much notation. Okay, so here's my question. I know nothing. Somebody please help me. Warren.
Change it to a proper prior.
Warren says change everything to a proper prior. So should we use a proper prior? Here's what will happen. Because the likelihood isn't going to pull down the tails, most of your statements are going to be through the prior. And so you're going to have to pick the hyperparameters. And I'm going to ask you for those, and I'm going to ask you what they mean. And if I ended up comparing my likelihood to my prior, I bet, or my posterior to my prior, I bet it looks a lot like the prior. So Warren's right, and I obviously set you up for this. But one solution is to go get a proper prior, but the artifact of this is your probability intervals are going to have just as much mass as your prior in a lot of places. So it might center it right. This looks centered correctly. But most of what I'll say about the interval mass and the probability will come through the prior. So, and my prior might speak too loudly if we do that. And so you would have to be very judicious in your hyperparameter selection. And convince me you had them for scientific or engineering reasons, everything worked out, and this works well. But I would say most of what you previously knew is what you know now. That one data point isn't supplying enough information. So I would not, even though I could get an answer. So I've seen that happen. Well, I got it. That's an answer. I get to interpret it that way. That's good. Just are going to have to argue those hyperparameters. So let's go for another solution. Anybody else got one? Yui. How about you?
No.
No. Zach, what would you do?
Go ahead.
Leading. Sarah? Stephen? Oh, make it uniform. Okay, so again, if I make my prior uniform, it's not going to be conjugate. I guess that's okay. It won't mess up my integrations because I'm just going to multiply by a constant, but I'm going to be truncating the tails off on this, and it's going to end up being the same problem that Warren has. So you're going to have to select that boundary. If you use the improper uniform, it won't work. Statistician, sitting in the consulting center. Somebody comes in, and they've got one data point. Let's just think about what they want to know. They've got this one piece of data. They have improper prior beliefs. You've got improper prior beliefs. You're like, I do not want to concentrate my maths with my prior and drive the whole analysis with this thing. So I don't want to come up with the answer just out of my prior. It can't do it on its own. I try to integrate over my priors, I get junk. Nothing. You know, it could be anywhere between negative infinity and infinity, and 0 to infinity is your estimate of the precision. So you've told them nothing. That's, I guess, good. They have one data point to supply you with, and they want to know the mean, and they want to know the variation. One data point, and you want to know the mean and the variance. Somebody walks in and says, here's one data point.
Use more data.
Use more data. Go get more data. Stop the analysis. The improper posterior here is really good news. It says you should not be able to tell them the answer with one data point. So I take this as almost a blessing. Like, good. Bayes is doing something important here. So saying you can't answer the question. With one data point, you might know a little bit about the mean, but you won't know anything about the variation. If you knew something about the mean, and you have one data point, that is informative about the variation. How far that data point is from the mean. And so if I knew the mean, one data point has information about the variation. If I knew the variation, one data point has information about the mean, but one data point on its own does not supply any information about both of those quantities jointly, and that's what we're integrating over. So, one data point doesn't tell us about, and I should say shouldn't, tell us about both mu and v. So hopefully you understand that point. You don't see any variation from one data point. So 2 data points is infinitely more valuable than 1 data point. If somebody gives me 1 data point, I'm going to say the answer is somewhere maybe around here. That's what I'd be willing to tell them. I don't know. I think your answer is concentrated somewhere around here. They'd say, well, how close to, I have no business telling you anything about could it also have been here or here because we don't see anything. So we're empiricists. We need to look first. If somebody shows me another data point, and I know you can't tell the scale right here, but imagine those are close to each other. And I would say, oh, cool, the answer is probably around here. Somewhere like that. And I might be willing to say something. And if all of a sudden somebody showed me this data point, a third one, it would wildly change my beliefs about things. But if I saw a third one just concentrate right there, that would be a lot of input. I have done an analysis with 3 data points. Those 3 data points were highly multidimensional. So there was information there, and that's about as low as I would go. So it's a genetics problem. So you could get 3. You know, it's hard to run evolution over and over and over again. Okay. 3 data points might have some information if they kind of all align and they're telling you something similar. So don't do inferences based off of things less than 3 data points, probably. I don't know, rough rule of thumb, but don't take it down to 1. So I'm just making the point that 2 data points is infinitely more informative than 1 data point, and 3 is a ton more informative. There's kind of this decay in how much information you're getting, but the first samples are telling you a ton of stuff. So prescription, get more data. I want to work through this integral right here so that we can come back and look at these steps again. And then I'm going to recognize this thing as a t-distribution for you. So we'll do a review next time. I'd like 10 minutes to tell you about t's up front, but I'm just going to work through the integral, and Stephen is right. With more than 2 data points, including 2, we will have a t-distribution. And so I'll write down for you just what a t looks like. T with new degrees of freedom. We need to discuss this distribution. Please don't ask me what degrees of freedom are right now. It controls tail behavior. I'll tell you about it later. It's a parameter in your model. Centered at mu with scale parameter sigma. I'll write it down as sigma. I could write it down as sigma squared if you wanted to. It looks like this. Gamma nu plus 1 over 2 over gamma nu over 2 square root pi nu. I had to look that up this morning. I don't know what the normalizing constant for t is after all these years, because I never use it. You usually don't do a degree of freedom estimation. So 1 plus x minus mu squared over the degree of freedom times sigma squared. This is minus degree of freedom plus 1 over 2. Let's talk about that next time. That is a t density. Lots to discuss. T's are usually what you base your inferences off of when you are marginalizing out variation. Okay, so let's just look at our new problem, pi mu. And we're going to go get more data. x1 to xn. So I've sampled down n times. And I'm going to write this thing down, is this is going to be equal to integral posterior distribution. I'm going to make it over phi. That's how I like to parameterize everything. D phi. So it's that same problem, 0 to infinity. Now I just need to write down what the likelihood is. So the likelihood for mu and phi, given x, times my prior, and I'll write it down like this, 1 over phi. This is pi mu times pi phi. They're my prior beliefs. Seeing more data should not change them. Should be the same thing. It's what I think. This is how I'm going to penalize my space, regardless of how much data I have. So the likelihood function just looks like this. I goes from 1 to n, and I could make this easier if I use the sufficient statistic, x bar, but I'd also need to use s squared, because I need both things in there. So I'm just going to do it kind of the easy way. This is going to look like phi to the half. I'll get rid of my root 2 pi, e to the minus xi minus mu squared. There's a phi in here, and there's a divide by 2. So that same likelihood function we've been playing around with the whole time. Now I'm thinking about it jointly. So let's just do this integral. It's not any harder than the first one we did. So this looks like this. I'm going to get rid of my proportionality, or my normalizing constants. This will look like phi to the n over 2. That's phi being producted n times. I'm going to absorb the sum. In here, I'll factorize out my phi just to make it easy. Sum of the I goes from 1 to n, xi minus mu, squared over 2. That still exists right there. D phi, 0 to phi. I've got my prior, 1 over phi. I'm going to absorb it right there. So that's my 1 over phi prior. So same thing as before, I just have n, and I've got n up here and here. And so this looks like a gamma. So I use the same notation, alpha tilde, beta tilde, where alpha tilde now looks like n over 2. N used to be 1. That helps us out a lot. This thing looks like this sum. Xi minus mu squared over 2. So pretty easy integral to do at the end of the day. I probably shouldn't have erased that. But this will look like this. This is beta tilde. This is going to be proportional to beta tilde to the minus alpha tilde. Just like before, the gamma alpha tilde is just gamma of n over 2. It's constant. So we have instant proportionality. And this looks like this. Sum of the xi's minus mu squared over 2. I goes from 1 to n to the minus n over 2. This answer is expressed in terms of mu. We can already start to understand this thing is going to be at least 2. These are quadratic under here. So this is going to be at least 2, so that'll be 1. This is quadratic. If you integrate under something quadratic, you get an answer. It converges. So I will tell you real quickly, this is a T density. You just can't see it yet. And that'll take us 10 minutes to walk through the algebra. But this is T. So here's a fact, and we'll do it next time when we come back. Fact. This is a T. The degrees of freedom. Anybody want to venture a guess? N. Anybody want to venture a guess? N minus 1. N minus 1 is correct. Anybody want to guess where it's centered? Okay, yeah, X bar. We all said the same thing. So sum of the xi's divided by n. Anybody want to guess where it's spread is coming from? What's that?
Sample variance.
Yeah, it's the sample variance. It's that S squared hat thing divided by n. So it gets scaled by n right here. So this thing again, sum of the xi's minus x bar squared. I goes from 1 to n, and this is divided by n minus 1. So I have to get those n minus 1s to magically appear in here. I need to get it centered around x bar. I need to do some factorization to make it all look this way. But we're going to work on this and chisel this into the form that I had written on the board previously. And I'll show you how to do that. I'm going to teach you how to do it in high dimensions also later on. So if you want to get ahead, go ahead and look at T distributions, see if you can work through this integral and get it there. But maybe also look at what a high dimensional T distribution is. And if you don't, I'll show it to you eventually. You guys have a great weekend.